All right, hello class. Um, let's do a couple more of these practice problems. I threw these together and I hope you saw them. There's a link to these in an announcement. There's also a link to these right on the home page. So if you haven't tried these problems, you should probably download them. There, that looks better. You should download them and do them before listening to me explain them. You're going to get a lot more out of it if you try to do them yourself. Take it like a practice quiz if you want to. They're just extra problems, not a practice quiz per se. But you really should do them yourself first. So again, don't just watch me do it. Really give it a go yourself. But with all that said, let's do it. By now, you should pause the video and do it yourself. Okay, so you tried it yourself. I hope you did a good job. Looking here, you should have pulled out an a value of 2. Well, I don't like that. You should have pulled out an a value of 2. I don't like that either. We're going skinniest. 2. You should have pulled out that your period was actually, maybe we'll do that work off to the side. Because if the b value is 3, then you know to find the period. For cosecant, we're still doing 2 pi divided by b. Remember, it's only tangent and cotangent that switched over to 1 pi divided by b. That's tangent, cotangent only. So we're going to end up with a period of 2 pi over 3. Hopefully that's clear to everybody. 2 pi over 3. Now, from there, from the period, I would hop right to the increment, because the increment is the period divided by 4. And 2 pi over 3 divided by 4 is the same as thinking of 2 pi over 3 times 1/4. You can see that that's going to be 2 pi over 12 or pi over 6. So we've got an increment of pi over 6. Now the phase shift, we got to get at the phase shift by factoring out the b value. So make sure you factor that out. It's going to be 3 and then, x minus pi over 3. So not a terribly difficult one to factor out, but don't tell me the phase shift is pi. You have to factor out first. So our phase shift is going to be pi over 3. Since we see a minus in the rule, we know that the phase shift must be positive, which means we're going to the right. Now our vertical shift tends to be the easiest thing. Well, I don't know. A is easy, but the vertical shift's easy too. It's the number that just is sitting there on the end, so it's 4. All right. Now we said we were going to have to come up with some scales, and we're basing our x scale, as always, on the phase shift and the increment. We're always going to base our vertical scale on the vertical shift and the a value. So that said, we need to pick a scale that works well for a pi over 3 phase shift and a pi over 6 increment. I usually like my increment to be 2 boxes if possible. That would mean going by pi's over 12, and that would mean that my phase shift is 4 boxes. Which is fine. The initial phase shift could actually be quite far if it wanted to be. And then we would use the increment. If we got pushed way to the right, then we could just backtrack to fill in the rest of our graph. So it's really the increment that you want your scale to play nicely with most of all. Especially, well, I haven't talked about this, so I won't talk about it. But increment, I'm going with pi over 12. All right, and the y scale can be 1. If we're going to go up by 4 and then up and down by 2, then going by 1 seems perfect. You could make a bit of a case to go by 2's, and then we would, if this was the x-axis, if we were going by 2's, we'd only have to go up 2 and then up and down by 1. And a bit of a case can be made for that because our function, cosecant, doesn't live in between here. It lives outside of there. So you'd actually be giving yourself kind of more room to plot the graph by making the middle region skinnier. I'm almost talking myself into it. I think I might wanna use a y-scale of 2 instead of 1. I'm not gonna. I'm gonna stick with 1. But hopefully you guys understood why there's actually kind of a strong case for going by 2 instead of 1. All right, all this said, now that you've got everything planned, you're gonna have to actually show me where your axes are. And if you put your x-axis right in the middle, you're a fool. Because we're getting phase shift, we're getting vertically shifted way up. Not way up, but 4 is pretty high. So we better drop this thing pretty far down because we're going to go up, what, 1, 2, 3, 4? Yeah, so we'd still have all this room down here for the lower half of our graph. Then from there, we're going to go up to, I think I like it pretty low. I might shift it up by 1. Again, let's not overthink that. That's not rocket science. That is what it is. We've got our phase shift. We said we're going to go right. We're going to go right by 4 boxes. So we should probably kick this axis over here a smidge. I think it probably wants to be there. I say smidge a lot lately. I wonder if you guys have noticed. It's kind of my new word, I think. So where are we going? We're gonna plot the vertical stuff. I like to do that. So we said we're going up 4, 2, 3, 4. So that's going to be our midline. Then we're going to get extrema 2 units up and 2 units down. I've also decided I'm going to call these things extrema. Local min and local max doesn't roll off the tongue so well. So I'm just going to call them extrema. But those are them. They're going to fall there. Now, our phase shift, we said we're going pi over 3 to the right. Well, our scale's pi over 12, remember? So maybe every couple of boxes, this would be pi over 6. We could go 4 boxes over and show that this is pi over 3. And then 4 more boxes would be 2 pi over 3. And then 4 more boxes would finally put us on pi. I think labeling those is a good idea. It sends a little stronger message as to what our scale is than just writing down the scale. We could show a few values, and we could do the same here too. So we're going to say this is 4, this is 6, this is 2. Then our scale is a little more obvious. Anyway, let's graph now. I'll graph in purple. To graph, we already said we're phase shifting, so we're phase shifting over to right here. Then thinking of your function, it's cosecant. Actually, it's negative cosecant. So, you should have it memorized that the graph is going to be the reciprocal of sine. Sine starts on its midline. So our function then will start on an asymptote. And it's reflected. So you could picture the sinusoid coming down and then up and then whatever. So that means our graph will start below the midline. Then you'll get another asymptote. Then you'll be above the midline. Then you get another asymptote. So this is the graph of a negative cosecant function. Again, it's just based off of what the sinusoid would look like as it snaked its way through here. So since we start on a midline, midlines turn into asymptotes. Then since the negative function would be reflected over, sine instead of going up to a max would come down to a min, which means we'll get a downward opening section here. Then the sinusoid would come back up, 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 but now it hits and we get an asymptote, and then it comes up, 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 and gives us another region that's opening up. That's it. If you can just memorize those rules, then the rest is very formulaic. So I think we just decided that there's going to be an asymptote here. And then our increment is 2 boxes. It's going to be 2 pi over 12s. So we'll go over by 2. And like we just said, we're going to want to be down below the midline. So we'll be here and we'll be here on the y equals 2 line. Then in 2 boxes, we'll have another asymptote. Then in 2 boxes, we'll be up at the point that's above the midline. So right here at 6, right there. Then 2 boxes. Then 2 boxes over asymptote. So here's 1 full period, but I did ask for 2 on this particular assignment. So from here we go over 1, 2, over 1, 2, asymptote. Then over 1, 2 boxes up to the point that's above, then over another asymptote. So now this is what 4 full cycles look like. The only thing left now is to make sure your curve looks good. Some of y'all gave me sinusoids that weren't looking so good, so you lost half a point, quarter of a point here and there, depending on how egregiously bad your curvature was. So you might want to practice, like actually put some time in, just making sure you can actually draw decent looking curves. But that's it. There's our function graphed. I know something people had questions about was, how do I write a new function in terms of the other function, in terms of secant, for example. So let's do that. If this thing's a of x, then let's say something, I'm not sure how to express this. Let's just go, I don't know why I'm hesitating so much. We'll call it f of x. And we know it's going to have all the same properties. For secant and cosecant, it could still be negative as we switch to secant. It could still be positive. It's really all in the phase shift. So I think I'll go for a positive secant. Why not? I don't like the negatives in front. We're still going to want that 3. I guess we want it factored out more than likely. And then we got this plus 4. Okay, well, translating one function into another is pretty easy when you've got the graph to look at. You just switch back into the mode of writing an equation from a graph. If I was writing a secant function, then I would choose as my starting point not this asymptote, that's the starting point of a cosecant function, but our secant function starts on what used to be a maximum value of the sinusoid, but what is now a local minima. But that point right there represents a perfectly good phase shift for us. That phase shift would be starting from nothing, so that's fine. And so where is this? It's right here. It's right between pi over 3 and pi. So you could take the average of those numbers. I think the easier thing to do is to mark off equal chunks. And then notice that if this is pi over 3, then this is pi over 6. And you're just counting by pi's over 6 now. So this is 1, 2, 3, 4, 5 pi over 6. So we can see that if we incorporate into our equation a 5 pi over 6 radian phase shift to the right, so minus, then I'm resting assured that this equation I just wrote called f of x is going to be completely equivalent to this equation up here called a of x. They'll have the same graphs. They'll have all the same values. So that's it. That's how you would write an alternate equation. And we said we definitely want to also do domain and range. So domain and range. I'm going to tackle the range first just because the range is easy. Basically think of it like this. You can see the range. You can see the range goes all the way up here. Our graph lives here, right? But then our graph does not live in the middle. But then our graph lives again from here to here, up, up, up. So basically our graph is all this yellow stuff. So it's negative infinity up to 2, that local max. But then anything between 2 and 6 does not exist. But then our graph exists again from 6 to infinity. So that is our domain. Just write that out. So the easiest way to write it, in my opinion, is just say I'm coming up from negative infinity. I achieve a maximum value at 2, and I do include 2. Then there's a big break. So we close our bracket, we say unioned with, then we see where we start up again. We start up again at 6, that local min. So we include 6, and we just continue all the way up to infinity. That's your range. That should be easy. I'm not supposed to say things are easy. That sets kids up. That sets you guys up to think that something's easy. And then when it's not, you feel bad. So, it ain't easy. If you're confused, you have every right to be confused, but come talk to me about it. I can explain it to you. For domain, we talked about this a whole bunch too. Hopefully y'all can see that this graph would continue all the way left. It would continue all the way right. So it covers most of the whole x-axis, but it's not defined everywhere. I want to say our domain is all real numbers, but it isn't, because everywhere that there's an asymptote, we have an exclusion from our domain. So we're going to have to say that it's all real numbers, but x is not allowed to be. And we said what we want to do is exclude the asymptotes. So pick literally any asymptote to sort of speak for all the asymptotes. There's one right here. It's at pi over 3. So I'm definitely going to exclude pi over 3 from my domain. Then I'm going to notice that all of these asymptotes are spaced out equally. And they're all spaced by not an increment. The increment walked me, from here to here to here to here. We're walking by half of a period, and it's always going to be that. So looking back up here, our period was 2 pi over 3. So half of that, rats. So half of that would be pi over 3. So this is kind of a dumb one. So if you write pi over 3 plus pi over 3 times k, then I hope you're recognizing that when k is negative 1, you get pi over 3 minus pi over 3, which is 0, which is guaranteeing you that there is another asymptote here at 0. So we should simplify that. I guess I won't order you to. But if you left your final answer as pi over 3 plus pi over 3k, that's a little redundant. We should probably just let that be 0, meaning we can just let that whole thing go away. And you could just give me the simpler expression, just pi over 3 times k, where k is an element of the set of integers. Now if you let k be 0, we get 0. That covers the asymptote on the y-axis. If you let k be 1, you get pi over 3. If you let k be 2, you get the 2 pi over 3. And of course, k as an integer can be negative. So if you let k be negative 1, then we get the asymptote that would be over here at negative pi over 3. We're going to get all of them. So this expression here is what's modeling our answer. So you got to give me exactly this. How do I possibly move just this over? Yeah, no can do. All right, you all don't need it moved over, right? Okay, I think I've done everything. I went ahead and I pulled out all the properties. I sketched a good looking graph. Everything that you see in lavender or the darker purple is the graph. I did write you a function that was using secant instead of cosecant. I addressed domain, I addressed range. And hopefully you guys got all the same answers I got. I want to get this video posted before it gets wicked late. So I'm going to move faster than I normally do, hopefully. So let's do this one. This one's cotangent. This one might involve me to slow down and explain a little bit because it's not secant or cosecant anymore. But let's hit the big tickets. We've got a as 2/3. Literally just pulling that value out of the equation. Nothing more to it. That's 2/3. Let's go ahead and skip over to the vertical shift because that's the other easy one. Let's do the front and the back first. Vertical shift is we're going down by 2. All right, what's the period? Well, the period is going to be, this time it is just 1 pi divided by b. That means it's 1 pi divided by 1/4. Well, again, I'm not going to divide by 1/4 when I can multiply by 4 instead. That's going to give me 4 pi. So this is a cotangent function that's been stretched out. So the period is 4 pi. That makes for a phase shift of 1 pi, because we're dividing the period by 4 like usual. That means our increment is our, put that in the wrong place. I don't know what I said. I did say phase shift, didn't I? Obviously I meant increment. The increment is going to be the period divided by 4. So the increment is pi. Our phase shift is going to come from up here. We do have to factor out that 1/4 again. Do not forget to do that. So you get 2/3 times the cotangent of a factored out 1/4, so times x, and then minus. Now we're multiplying by 4. That makes 6 pi. And then a minus 2. So we've got another pretty big phase shift, and that's fine. 6 pi. Great. Love it. All right, so how do we handle this then? Pretty sure I still want to look at my vertical dimensions, which are a and the vertical shift. I might have made this one a little weird. All right, with an a of 2/3, we see that we really can't go by much of anything on the y-scale other than 1/3. If I go by 1/3, then my a is going to be 2 boxes at a time, pretty obviously. But what? This thing is going to be 6 boxes. So the vertical shift. I think that's fine. We'll just have to throw our x-axis way up near the top because we know we're getting vertically shifted down by 6 whole units, and then we're only going up and down from there by 2. So we can concentrate ourselves right in the middle where we need to be. So now, right, So now, focus on your horizontal measurements. I can't even pick a color. Which would be your phase shift, which is pretty big, and your increment, which is pretty small. So we said in the last problem that I would like for the increment to be maybe 2 boxes at a time, so going by pi over 2 would seem wise. But if we went by pi over 2, then our initial phase shift would be 12 boxes. I did have someone point out in class that there is a hell of a lot of boxes here. So phase shifting 12 boxes to the right, that kind of seems fine, doesn't it? I think there's room for it. So you know what? I'm going to do it. I'm going to go ahead and go by pi over 2. Sure. So that just rendered this as 12 whole entire boxes. And that meant that this is now 2 boxes. So we got plans. We can move our axis way the heck over, first of all. That gives me room now to phase shift way the heck over by 12. And I think we also said that I want to push the y-axis pretty far up too, because we need room below the axis. So I'm going to try putting it here. I'll think that through a little bit better, but that seems good to me. So checking the vertical stuff, we just said the vertical shift is 6 boxes down. So maybe this top line should be up a little more so we could cheat this up, but we're okay. Because our A value is only 2 boxes up and down. So we'll go up by 2, down by 2. And the more I look at this, the more I don't like it. So maybe I'm wrong. Maybe we should drag this down. Like if we just put it here, then our graph would be more in the center. So you might want to do that. I don't particularly care, so I'm not gonna. But now let's get our horizontal stuff in order. We are gonna phase shift 12 whole boxes over to 6 pi. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's 6 pi. And we are going to go ahead and plot our first point there. Cotangent, we know, has its first critical value on an asymptote. So this is an asymptote. But from there we just follow the general trend. We are a positive cotangent, so we will be decreasing, which means the point that comes right after our initial phase shift, it's going to be 2 boxes later, and it's going to be up above the midline. So yeah, we're going 2/3 up and down. So we're going 2 boxes to the right. So we're just kind of going over 2. And we don't want to be on the midline, we want to be up here above it. Now we'll go over 2. There's that midline value. Now we'll go over 2. Here's my point below the midline. We go over 2. And then we're done. You know, kinda. Because now we are supposed to check this thing. Again, you should be curving under and then up through. I should see the first branch as concave up, but the second branch, that's completely different. That guy should be concave down. This is ugly, but I don't think ugly enough that you'd lose points. So your options now are just continue building out to get a second period, or come back here and build backwards to get a second period that's closer to the axis. I'm inclined to do that. So again, if I were you, I might make a little marking that says, yo, that thing right there is my starting point. Then you can build all over wherever you want, and you're going to remember where your phase shift is because you marked it. So we want to keep graphing. So we said our increment is 2 boxes at a time. Yeah, so we're here. We'll go 2 boxes over, and we should get another point that's below the midline. Then in 2 boxes, one that's on the midline. Then in 2 boxes, one that's above. Then in 2 boxes, another asymptote. That looks bad. That looks really bad too. But anyway, there you go. There's my graph. It's not good, but all the points are in the right place. So what else did I say I would do with you guys? I think we're going to always want to be thinking about rewriting the function in its companion function form. Write the domain, write the range. So I will do all those things. If we're going to write a tangent function, then one way to think about this that I taught you was just don't change anything. Okay. Still keep the 1/4 factored out, so it'll be minus 6 pi. Then leave some space for the phase shift you're going to need, and subtract 2. The equations should be almost exactly the same, but there's two things that have to change that we talked about. This tangent function as written would be increasing. And so for it to match our function, we need it to be decreasing. It needs to be coming down. So to get that, we'll just put a negative value on A, and then it will get reflected. To fix the other thing that we don't like about this is, with the 6 pi phase shift added in here, then we would translate over to 6 pi, and our graph, the first thing we would plot would have been a point here, and I guess would be down because we're using the negative, so it would be down. So we get a graph that's, you know, really, really similar to the other, but it sits in the middle of them. So how do you get these guys to line up? You just push it to the right or you pull it left. Either way, it's gonna coincide, and all the other little chunks are gonna end up coinciding with the others too. So a simple phase shift by half of a period should get these two graphs back in sync. So with a period of 6 pi, we're gonna add on 3 pi or subtract 3 pi. If we subtract 3 pi though, then we're going all the way over to negative 9 pi. If we're trying to stick close to the axis, then negative 3 pi seems better. So your final answer would be negative 2/3. So same A value, but tangent needs to be negative. The 1/4 would still be the 1/4. That's based on the period, which hadn't changed. X is X. We can actually do this operation. It'll be minus 3 pi. Minus 2. Yeah, that's your equation. So now just domain and range. Again, I'll get the easy one out of the way first. And that's the range, because the range is just going to be all real numbers. The domain, though, is again going to be all real numbers except for these asymptotes. So it's going to be all real numbers, comma, x may not equal. And then we're looking at it. What can't we be? We can't be any of these asymptotes. So the first asymptote that we plotted, which I guess is here, if that's 6, comma by pi is over 2. Yeah, okay, great. So if all of these are pi over 2, then this is 1, 2, 3, 4 pi over 2, or 2 pi. And then the next one we care about is what? 1, 2, 3, 4, 5, 6, 7, 8 more. So it's 8 pi's over 2 later. Yeah, I'm dazing out. I'm really tired. I don't know what I'm doing. Obviously what I'm counting off is the period, which we already knew was 4 pi. I don't know why I'm doing that. Yeah, all right, I'm trying to find this asymptote, and it's 1, 2, 3, 4. It's, oh yeah, I labeled it down here. I'm really getting out of it. I gotta wake up. All right, so here we go. We've got a bad asymptote at 2 pi. And we said we're gonna add on to that half of the period, which is 2 pi, which means we're bumping into the exact same problem from the previous problem. So I apologize, it just happens like that sometimes, but if you remember here we had 1/3 plus 1/3 pi k. That signals that your critical value is just at the origin. And I guess we did that again, and by we I mean I. Yeah, it was my bad. But yeah, if we kept drawing asymptotes, we would not get one here. Oh boy. I'm wrong about something. Okay, let me try to figure out what I'm wrong about. I think naming 1, 2, 3, 4. Naming this asymptote certainly seems fine, and it would be 4 pi over 2, which is 2 pi, so I like that. And we definitely want to go half a period, don't we? To get from asymptote to asymptote? Yeah, so that's 2 pi 2. Alright, I don't care. I'm going to live with it. So 2 pi k, where k is an element of the set of integers. And so again, I do believe we should be able to get rid of that. I'm not sure why my eyes are deceiving me here. Maybe I graphed it wrong. Did I graph it wrong, guys? Increment is pi? Yeah. Okay. I got it now. I'm being silly. I'm sorry, and I wish I could just edit this out, but I don't know how to. So I'm just being a dum-dum. From asymptote to asymptote is not half of a period. It's a full period. I think I was thinking back to the other graphs. Asymptote to asymptote here is half of a period. But for the tangent function, asymptote to asymptote is a full period. So I'm not adding 2 pi, I'm adding the full 4 pi. And that means that everything here is hunky-dory. So this is now correct. I apologize for having that take 100 years. Oh, and cool. I did that too, where I left my face in the way. Forgive me for that as well. Face can go over there. Alright, but here now is everything. I made such a nightmare out of this. Sorry, here's everything. So here's the finalized equation in terms of tangent. There it is. Here's the final domain, and here's the range that I got. Sorry. Moving on. So now I have a few of these graphs. I really didn't like the graphs from your homework, so I'm giving you some very clean ones, the cleanest I can come up with. And you guys got to write equations for these. So again, if you haven't tried this yet, then pause the video. Try it right now, and I'll walk you through it. So if you're back, it's because you already tried this. So let's do it. So over here, right underneath my face, which is here, let's grab our values. We should be able to find A relatively quickly. We can find B somewhat quickly. C, we said we're really not going to find overall, because C varies from between the function type that you choose to use, but D is always the same. So we can find A, B, and D super fast. So looking, I certainly see my local minimum is right here at 6. My local maximums are right here at what I guess is -2, right? So the total distance between 6 and -2 is 8, and half of 8 tells me my A value, so it must be 4. Then also, if I went down 4 from 6, it would land me at 2. That's telling me that 2 is my midline. And if 2 is my midline, then 2 is my D value. So there's your vertical stuff sorted. It took about 1 minute to sort all that. Now for the B value, we get the B value from the period. So we got to get that period. And I guess my preferred method here would be I don't know. Probably the best bet would be focus in on this local min and this local max. And then I think you guys can see, I think most of y'all seem to understand what I was saying here. But if I took this point and dragged it left 1 unit, then I could take this point, drag it left 1 unit, and everything would still be lined up where it's supposed to be, right? And that makes it real easy for me to see that the distance from 0 to 3 pi is 3 pi. Now that's not our period though, because our period should have gone from one of these local extrema all the way to the other one. So what we just did by going from min to max is we found only half of our period. And if half of our period is 3 pi, then a full period is 6 pi. So there, we did it. Now that thing being 6 pi implies that our b value is 2 pi divided by our period, which is 2 pi divided by 6 pi. So the pi's cancel first, then you can cancel the 2 with the 6 to just get 1/3. So that's our b value. Alright, so we now have everything. So to write a secant function, it'll be 4 times the secant of 1/3 times x with some phase shift. What's the phase shift? Well, if you're writing a positive secant function, then again, I urge you, visualize the sinusoid that runs through this graph. So the midline point should have been here. I botched that, don't look at that. Midline, min. So we've got this sinusoid that's running through. I'm not sketching it very well at all. That's kind of hard to draw. But if secant is associated with cosine, then if you're trying to write a positive cosine function, then you're looking for where your function had a max. That would be right here. So this point gives us the phase shift for a positive secant function because it gave us the phase shift for a positive cosine function, and those guys are related. Okay, so what's this right here? Well, I see 1, 2, 3, 4 boxes that come together to make up pi. That would seem to tell that this indication right here is pi that has been divided into 4 equal parts. So our phase shift is pi over 4 to the right, which is minus pi over 4. And don't forget the plus 2. But that ought to do it. That's one function. We need a second function. So you just go with cosecant. No, doesn't have to be negative. Okay, so here's everything but the phase shift. Well, cosecant is still going to be based off of our sinusoid, but it's based off of the sine function. So where our sinusoid was on the midline is where our function needs to be phase shifted. So, you know, this is a good one. It's a little closer than this one. We could use we could use either. I'm going to use this one. So again, we're counting by pi over 4. So here's 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. So we're going to phase shift 5 pi over 4. And since we're going left, we have to say plus. But now that's really it. That's 2 equations for the one graph. Can we do domain and range quickly? Sure we can. Let's move the face. Okay. So domain, I hope you're catching on by now. Domain's gonna be all reals. But x cannot equal. You know the drill. Pick an asymptote. I think I'll pick the first positive one, even though it's a little bigger. So here's pi, that's 4 pi over 4. 5, 6, 7 pi over 4. So 7 pi over 4 is an x value that needs to be excluded. And all the other x values occur half of a period later. I know I just flubbed the cotangent one a minute ago. But I'm right this time. We really do want to space these asymptotes by half of a period for secant and cosecant. So our period was 6 pi. Half of that is 3 pi. So you're just going to add on 3 times pi times k, and then stipulate that k has to be a nice clean value. So you'll say k has to be a nice clean value called an integer. It can be positive or negative. So as we talked about before, when we let k be positive integers, we're adding on the 3 pi, and that's pushing us forward to the next asymptote and forward to the next. But when we let k be negative, we're adding a negative. That subtracts. So that's what pushes us backwards onto this asymptote and excludes it. There's another one over here. We're going to eliminate that guy too. But so that's what this notation means. I'm going to stop explaining it now forever. All right, what's our range? Range, we said, negative infinity up to some value. Union, some value out to infinity. So for our function, what are those values? Well, the values would be that if we're coming up from below, then this value here is the important one, and it's located at -2. So that means our domain is going to stop at -2. We're never going to get any higher than -2. We've got this weird empty space, but actually the graph does pick up again once you get to 6. So from there you'll go from 6 to infinity. There you go. There's the whole kit and caboodle, and we'll do another. So I actually gave you 2 of everything. Okay, so here's a second tangent cotangent. Oh God, I'm too tired to live. This is not tangent cotangent. This is secant cosecant. And I've given you a second secant cosecant. Then I've given you a tangent cotangent. And another tangent cotangent. We're already at 40 minutes. So that I can get this video out at the time that I said I would, I'm just going to stop and upload this half right now. And I'll put out the other half. The other half should be out by the time you're done with this half. Good studying, y'all. Good luck tomorrow. Bye.